Hello, this is the second part of the video about multiples of vector spherical harmonics. In this video, I will talk about their topological charges or Hopf indices. But before we move on to the multiples, let's consider a simple smooth vector field in 2D plane and learn how to calculate its Hopf index. We will consider a vector field that has an isolated zero, as in above pictures. Let's take one of these fields and calculate the Hopf index for that zero. To do this, we will draw a contour around the zero, and we will go around it counterclockwise. We will keep track of the orientation of the vector field during this way. Note that this vector makes two complete rotations by 2p. In addition, the vector itself rotates counterclockwise. This means that the index of such vector field equals 2. If we consider another vector field, such the one depicted here, this vector will now rotate clockwise. Then we go around the contour counterclockwise, which means that the index is -2. Recall the vector fields we saw in the beginning. The indices of these zeros are also easy to calculate using the same algorithm. Now I will talk about one consequence of the Poincar-Hopf theorem, which is called the Hairy-Ball theorem, and in some countries also Hedgehog theorem. In this case, smooth vector fields are no longer considered on the plane, but on sphere. It turns out that for any vector field on sphere, the sum of indices of all its zeros is always the same and equal to the Euler characteristic, which equals 2. All multiples, as we know from the previous video, are exactly smooth vector fields on sphere. Let's check now how this theorem works for an electric dipole. Indeed, it has two zeros and indices of both equal 1. But for magnetic quadrupole, there are two zeros with indexes -1 and four zeros with indices +1 on sides, and the sum is still 2. Actually, the indices of individual multiples are easy to find, and this is done in the paper linked at the bottom of the slide. For applications, the most interesting indexes are of those zeros at top and bottom of the sphere, in other words, on the z-axis. This may be interesting in the context of topological charges of bound states in the continuum in metasurfaces. For any eigenmode in a metasurface, one can write a multiple decomposition. It is done for the currents of individual meta-atoms and describes how a meta-atom with such currents would irradiate if it were alone. But the topological charge of the bound state in the continuum can only be one of the topological charges or Hopf indices of the multiples, of which this eigenmode consists. More precisely, equals to the index of 0 on the z-axis of dominant multiple. Moreover, it turns out that there are special linear combinations of multiples for which we can get any index in this up or down direction. To do so, we need to take the Kerker multiples, or in other words, the real parts of the combinations of multiples with certain value of helicity. On this, you can find more information in previous video. Namely, it is the sums of kind of crossed electric and magnetic multiples with the same numbers, M and L. Here in the figure are the sums of real electric and magnetic multiples with total angular momentum 4 and different number M. And one can easily check visually that the indices of such zeros have a simple dependence on the number M. Thank you for watching. I hope this video was useful. Please subscribe to the channel to see another videos on photonics.